So this is topic 3, and hopefully you're watching this more or less right after topic 2, because these two should really go together. In the last lesson, I would have shown you how to find areas under a curve by using boxes. And there's many different ways that you could do this. You could work with boxes that are all a little bit too small. If you can kind of see all these rectangles I'm drawing here, just a little bit too small. Now, that would be, in this example here, that would have been my left-bound rectangles. You also could use rectangles that are all just a little bit too big. And these ones in red I'm drawing are right-bound ones. And what I prefer to do with Riemann sums is average the left and right, and that should be pretty close to the actual area in terms of like using boxes. Now, I've also seen this done using an actual, like, I believe it's a trapezoid is the shape. Whereas rather than doing this, you do the shape like this, and you'd make it like a, well, a trapezoid should look like this. It should have a side like this, and then maybe like a triangle-looking piece like that. That would be a trapezoid type shape. I didn't draw it very well. Let me see if I can do one better. Is there a trapezoid in this thing here? Well, yeah, not exactly. This is a parallelogram of some kind. It's almost like I need it to look like this, except what I have to do here is change it so that this side right here is like a perfect square. If you could like eliminate that, that's kind of what you're looking for. Right. Long story short, you can approximate, and I want to use the word approximate here, the area under a curve using a method like this, but that's really not exact. So what I want to do today is just continue by showing you how you can find it exactly, and really you're just using the fundamental theorem of calculus. To find the area under a curve from A to B, find the antiderivative from A to B, plug in those values. So let's do an example here. Let's find the area under the curve for 2x plus 3 from 2 to 5. So this is really saying start at 2, end at 5, antiderive 2x plus 3 with respect to x. And so when you do that, it's going to give you 2x squared over 2 plus 3x from 5 to 2. Well, really, that's just x squared plus 3x from 5 to 2. So plug in 5. Subtract what happens when you plug in 2. Let's see what we get. That'll be 25 and 15, which is 40. This will be 4 and 6, which will be 10. So my final answer should be 30. The area of this thing should be 30. Now on this one here, I said, let's actually confirm this with our knowledge of shapes. Because really, I mean, this isn't technically using Riemann sums as much as just using geometry. Riemann sums would be an approximation, but I should actually be able to calculate this, knowing what a triangle works like. Because 2x plus 3 has a y-intercept of 3, a slope of, let's call it 2. And so this should really create, from wherever I'm looking here, it should create 2 distinct shapes. Now, I believe I went from 2 to 5. So really what it's going to create is a triangle and a square. So the first one is a triangle. The second one is a square. Your triangle is 1/2 of base height, and your rectangle is length times width. So to figure out the square, that one's easy. The length is going to be 3, because that's how far it is from 3 to 5. I do need to figure out how tall it is, which means I just need to know what this value is right here. And very similar to last day, I just need to know what f of 2 is. Right? F of 2 is how tall this guy is. So let's see, what was my original graph here? It was 2x plus 3. So for 2 times 2 plus 3, that would be 7. So 3 times 7 means that this guy right here should have an area of 21. Now, for my triangle is 1/2 base height, which is 1/2 of 3 again as my base from 2 to 5. I need to figure out my height. Well, my height is really just from here to here, so to figure that out, I should really solve for this point. But this point right here is f of 5. So 2 times 5 plus 3 would give you 13. So if up to here is 13 and up to there is 7, it would seem that my height is 6. So 3 times 6 is 18. Cut in half should give you 9. Well, if one box is 9 and the other box is 21, if I were to add them together, that would give me 30, which is exactly what I got right here. So now this is a nice little proof for how shapes work. Now the problem is that not every single shape is got like a nice square edge to it, right? What happens if the shape that you're working with is all curvy all over the place? You really can't use a triangle. You can use Riemann ideas and just use like really narrow boxes, but fundamental theorem of calculus works way better. So let me try another one here. What if I gave you this function here, but I threw a little twist in? Rather than telling you go from 1 to 5, I said go from 1 till b, an unknown value. Well, I mean, we can still do the exact same thing. We can go from 1 till an unknown value of b for x plus 1 dx. And that dx, as I've been saying, is really important because when I antiderive 1, it lets me know what variable to use. Because this is going to give me x squared over 2, and then this 1 right here will just turn into x, because I know that I'm going from dx there. Well, then the only thing I have left to do is plug in from b to 1. So I'm really looking for b squared over 2 plus b minus 1 squared over 2 plus 1. Now, I need to clean this up a little bit here. That's a pretty reasonable expectation. So I'm going to times by 2 over 2 right here. I'm also going to times by 2 over 2 right here. And this should give me b squared plus 2b. And then right here, 1 squared plus 1 more. Well, 1 squared, this is really a 2. 1 plus 2 would give you 3. So you're going to minus 3. All of that's over 2. There, this is what your area is equal to. So I guess one other way of writing it is it could be 1/2 of b squared plus 2b minus 3. And I mean, it really depends on what you're looking for here, because let's say you wanted your area to be equal to 0, for example. I know that's not your question, but say it wanted your area to be 0. Now, the first question you'd have is, how do you have your area be 0? Well, it could be because you end up having a graph like this, where some of the area is above the x-axis and some of the area is below the x-axis, right? So that's one way it could occur. Anyways, the reason why you might think to do this then is that, look, this guy was factorable. It'll give you b plus 3 and b minus 1, which means that b would either be either 1 or 3, or negative 3. Well, now hang on, b being 1 makes a lot of sense. You know how you have no area? Is if b is 1, well, if you go from 1 to 1, literally you're not even moving anywhere on the graph, so that would give you no area. And now if you went backwards to negative 3, what you're really needing to do actually is go from negative 3 to 1 is really what that means. And if you did that, if you know what x plus 1 looks like, this is x plus 1, if you go back as far as negative 3, and you go forward as far as 1, then yeah, your positive area and your negative area would cancel. So anyways, that wasn't really the question. The question wanted to know what your area was, which means you could have stopped here or here. I was just extrapolating a possible question you could get asked from that. So, well, let's try another example here. Let's try to find the area under the cosine curve exactly using 0 and pi over 2. And you've got a couple of questions like this on your assignment, by the way, where I'm going to ask you to find area under cosine or sine. And the reason why that's so useful is that sine and cosine, there's a couple of things you need to know. If this is a sine graph right here, first of all, this area right here is not going to be a nice regular shape, right? Like this has got a definite curve to it. And so we can't really use the box method all that well, right? I mean, it's possible, but it's nowhere near as easy as knowing your antiderivatives. And the other reason why is that sometimes you'll have some area under the curve as well. Now, generally the way this works is that area is considered to be everything from your line to the axis. So here you'd have some positive, here you'd have some negative, here you'd have some positive. So like we actually are going to have alternating areas going on here. So okay, anyways, moving back on. Let's try this here. We want to go from 0 to pi over 2. We want to antiderive this. And so if we do that, then we need to antiderive the cosine graph. And the way that works is that it's actually sine, right? The antiderivative of cosine is sine, because sine derives to cosine, but then you're going from 0 to pi over 2. So we need to do the sine of pi over 2 minus the sine of 0. Well, then you just need to know what sine of pi over 2 and sine of 0 are. That should actually be a 0 here, 0. So here's your regular sine graph. Sine of 0 is 0, and sine of pi over 2 was right here. Pi over 2 is 1. So 1 minus 0 gives you 1. So that means that on your cosine graph, you know how your cosine graph looks like this? Right here, that's pi over 2, and that's 0 right here. Essentially what I'm telling you is that that area right there, this is really cool. That's an area of 1 from there to there. I mean, logically, this would mean that from here to here is also an area of 1. So if this was 1 and this was negative 1, now remember this is at pi, right? Pi is the halfway point on this graph here. Then it should be 0. So I just want to try that real quick here. What if we did the exact same thing, but we did the antiderivative from 0 to pi? So this should give us a positive area of 1. This should give us a negative area of negative 1. So in theory, I'm expecting a 0 answer. So again, this would be cosine x dx. So I went from, well, let's not do that. That would give you sine x from 0 to pi. So we need to do the sine of pi minus the sine of 0. But again, sine of 0 is 0, and sine of pi is 0. So this actually makes sense. You'd actually have no area. Now, I mean, you got to think about this for a sec here. From here to here, this one looks like positive area, but this one here is negative area. They would cancel each other out. So there, you'd have no area left. So, well, let's try some more examples here. What if I just changed the question here and I just said, find the area of the region below y equals 4 minus x squared bounded by the x-axis? Well, we normally do things with the x-axis anyways, right? That's usually how these area formulas work. If it's below the x-axis or above the x-axis, it just changes its positive or negative. But I just want to graph this guy real quick here. A negative x squared plus 4 graph would look like this. And so we're really looking for this bit right here. But what changes this question type is that I didn't tell you where to start or where to finish. Which may mean that one of the twists I could throw into a question is that first you need to calculate the start-finish values. Right? We know we're going to antiderive 4 minus x squared with respect to x, but I have a question mark for where to start and finish. Well, then, I mean, here, this is just some basic grade 10 factoring. 4 minus x squared, we need to make it equal to the x-axis, which is a y value of 0. So this will be 2 minus x and 2 plus x. Which means that x is going to be 2 and negative 2. And now I know where my start and finish values are. Which hopefully you didn't need a whole lot of help with trying to figure that out. But I just want to point out here that I may not tell you where start and finish are. I might just expect that you can do that. So, okay, so I mean, based on that, then the next thing we just need to do is antiderive. So this will give you 4x minus x to the 3 over 3, plugging into a negative 2. So 4 times 2 minus 2 to the 3 over 2. And then I'm going to subtract from that 4 times minus 2 minus 2 to the 3 over 3. This will give me 8. This will give me negative 8 with an extra negative will give me plus 8. This is going to give me negative 8 over 3. All right, this one's a lot of work here. Negative, negative, negative means it's positive, and again, it's 8 over 3, actually, right? Negative, negative, negative. This guy should be positive 8 over 3. Those guys should cancel. I got a final answer of 16. So that means that the area right here was 16 units. So, okay, I haven't said this a lot in the last couple of videos because, I mean, mostly because you guys don't take me up on it, but make sure you ask me questions. Make sure you get some help because we're getting to the point where calculus gets a little bit more challenging, a little bit trickier. And if you ever hit that spot where you're like, whoa, I didn't get that, make sure you learn how to ask, okay? Well, what we can also do then is figure out areas between, oops, what am I doing here? There you go. We can find out area between two graphs. Like, for example, what if I wanted you to find the area between these graphs right here? not between the graph and the axis, but between the graph and another graph. Well, I mean, the way you just solve this then is you'd subtract the areas. You find the area of the big graph and subtract the area of the little graph, right? Let's say that black is what I wanted to solve for. I'm just going to pull black off to the side for a second here. To solve this otherwise, what I could do is I could find the area in the exact same section here for f of x all the way down to the axis, and then I could subtract the area from g of x all the way down to the axis. If I took this guy right here and subtracted that little bit, it should leave me with the other one here. Now, I didn't really draw this all that well, but if I pull this off of there, it should give me this one. Wow, that really was not my best drawing ever. Does that make sense, though? This plus this should equal that one. So if I subtract this one and go this one minus that, it should equal there. So long story short, find the area of the taller graph and subtract the shorter graph. Now this does raise one interesting point though. You have to know which one is bigger than the other one, right? You have to know who to subtract from who. You can't subtract g from f if g is littler than f. So you do have to know which one's bigger. But I mean, this is pretty straightforward. Let's try a graph here. Let's find the area between the graphs of x squared and a half of x. So for a quick little picture here, I know what an x squared graph looks like. It looks like this. And then 1/2 x looks something like that. And we are looking from 1 to 3. So let's say that 1 is right here, and that 3 is right here. 1's right there, 3 is right there. Hopefully it's clear that the x squared graph is always greater than the 1/2 x graph. So if I want to find this area right here, that is kind of the black area that I put here. Let's try to do this one better than last time. If I want to find that area right there, the way I find that area is by finding the entire area down to the axes of the larger graph and I'm going to subtract the area of the smaller graph. And if I subtract them, green minus purple should equal black. And you should even be able to see that now when I put them together, right? These things should approximately be the same area. So if I want to find this black area right here, I find the green area, I subtract the purple area. So here's how that looks then. I need to find capital F of x. Let's make this f of x right here. Let's make this g of x right here. And I have to subtract capital G of x. I need to find the area of the first one and the area of the second one. Okay, so that's not so bad. Let's just do it one at a time. I want to antiderive from 1 to 3 x squared. And then when I'm done, I want to antiderive also from 1 to 3, 1/2 of x. And in both of these cases, my variable is x. X squared becomes x3 over 3 from 1 to 3. And 1/2 x becomes 1/2 x squared over another 2 from 1 to 3. Which I could really rearrange and just make this x squared over 4. Okay, so then this means I need to go 3 squared over 3 minus 1 cubed over 3. This is the area of f of x. And I have to subtract from that the g of x area. So I need to subtract 3 squared over 4 minus 1, actually that's 1 squared. Yeah, 1 squared over 4. Okay, well, 3 squared is 27 minus 1 is going to be 26 over 3. This is the area of the large graph. And this is going to be 9 minus 1, which is going to give me 8 over 4. Which 8 over 4 is really just 2. So this is the area of the big graph. This is the area of the small graph, right? Even the 2 makes sense. Doesn't it? Shouldn't 2 be kind of the area from 1 to 3 right here? From 1 to 3, 2 is 1/2 of 4. 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 2 is 1 let's just check that here, right? From 1 to 3, you're 2 units across, and you really have a square and a rectangle. Now, at 1, the value would be a half, so this would be the square would be 1/2 by 2, which would be 1. So that's the rectangle. And the triangle is 1/2 of base height. Again, the base is 2. And then your height, I believe, at that point is 1, because this is going to go over 2. And in the point it goes over 2, it goes up 1. So that's another 1. So that's 1 and that's 1. It gives a grand total of 2. So anyway, long story short, to put this all together, you've got 26 over 3 from one, 2 from the other. But 2 can really be, say, 6 over 3. So your final answer is 20 over 3. That is how much area is now between the curves. So to find the area between these two graphs, which was what I drew in kind of black right here way back when, find the area of the big graph, subtracting the area of the small graph. It's actually very straightforward. The issues arise when I don't tell you which graph is bigger than the other one, and you need to know which one. Or maybe I don't tell you where to look, like say on this one right here. I'm just going to say, find the area bound by these curves. Well, if you know much about these graphs, the x squared graph looks like this one right here. The other graph right here is a negative x squared plus 2x graph, which means if you factor it out, there's a negative x and then there's an x minus 2, meaning you have a root at 0, and then you also have a root at 2, and this is a graph that's upside down, and so it should look something like this, which means that the area you're looking for is right in there. Now, if you're able to follow that, I actually know where my start value is. I need to antiderive from 0, because 0 looks like it's where they cross, but I actually have to figure out, well, where do they actually intersect over here? Well, so if I don't know where the upper limit's going to be, I need to do a little bit of work first. I need to figure out where x squared is equivalent to 2x squared minus x squared. Well, this is quadratic, so if I bring everything to one side, I could give you 2x squared minus 2x equals 0 by swinging everything that way. And then if I factor, take out a 2x, it leaves me with an x minus 1. It means that they cross when x is 0 or 1. Now, 0 I already knew, because I could tell they both had an x-intercept at 0, but it appears that they cross right here at 1. So now I can proceed with solving the rest of the question. I need to antiderive, now that I know this, from 0 to 1, and now I need to know which graph is taller. Well, the graph that's taller was the purple graph, which is the 2x minus x squared graph. So I'm going to find that area with respect to x. And I'm going to do the exact same thing from 0 to 1, only now I'm going to subtract off the x squared. So if I find the bigger area in purple and subtract the smaller area of the red graph, I'll even draw that in. The red graph would have some area right here, up till there. If I subtract the big purple, the purple would include the red, and subtract off the red, I'll have my answer. So here we go. Again, I'm kind of blitzing through these antiderivatives at a higher rate of speed, because I do kind of assume that you know how to do this. But if you have questions, please make sure you ask, okay? So we're doing that from 0 to 1, and then we're doing this from 0 to 1. So this is really just x squared. So we need to do 1 squared minus 1 to the 3 over 3. And then I have to subtract 0 squared minus 0 to the 3 over 3. But hang on a sec here. Isn't 0 squared minus 0 to the... like, that's that. Don't bother with that, right? And then I have to subtract from that. So all of this then needs to get subtracted from 1 to the 3 over 3. Minus 0 to the 3 over 3. Okay, hang on a sec. 0 to the 3 over 3 I don't need again either. So, I am going a little fast here. This is not an x. That should be a 1, though, shouldn't it? There we go. Okay, so to recap here, I've found the area of my big g of x graph, and I'm going to subtract the little f of x graph. Now, in each of them, because we were starting at 0, it just kind of works out nicely that I can just kind of eliminate the whole 0 option here. So let's finish this off. That's 1 minus 1/3. And then right here, I have to subtract another 1/3. Well, 1 minus a third minus another third actually gives me an answer of a third. So it means that right in here, that little purple area right there, that must be 1/3 of a unit. Okay, so quick recap on how to solve a question like this. If you don't know where they intersect, if it doesn't tell you that, make the two graphs equal to each other, then find where they intersect. Now you'll know your lower limit and your upper limit. Then you can anti-derive both of them. I missed a dx right here, by the way. You can anti-derive both of them, plug in the zeros and ones for both of them. The biggest issue here is just keep track of your work. Make sure that you're organized enough that you and I can follow it. So, I mean, I was a little bit messy here with canceling this bit out. If that loses you as to why that was valid, make sure you ask, right? So, all right, I got one last example. I want to find the area between cosine and sine. Right? Now, I mean, if you know what these graphs look like here, sine looks like this. Right? And cosine looks like this. That's sine and cosine. Basically, sine is cosine just offset by pi over 2. Well, I mean, now I'm looking for the area between these curves, which means right here, I'm looking for that area right here. Like that. And then I'm also needing to find the area of the other section here. Now, pi over 2, by the way, is right there. So I need to find this area right here. So I actually have two little snippets here. The reason that makes this question more challenging now is that for part of this area that I'm looking for, purple is bigger than red. And then for the other part of the area, red is bigger than purple. Hopefully that makes sense here. We need to figure out two different sections here because there's a section where the cosine graph is greater than the sine graph. But then there's also a section where the sine graph is greater than the cosine graph. So we have to do this in two sections. Now, it really looks like this is symmetrical. So it may be the same thing times by 2, but I should really confirm that. So the first thing I really need to figure out, though, is, well, where do they cross? Where is the place where cosine equals sine? Where are they equivalent to each other? Where is this location right here? Now, I mean, hopefully this is just something you know from your Math 30-1 course, but sine and cosine are the same as each other when you have a graph that's 45 degrees. If you have a 45-degree triangle, which is like 1 root 2, sine and cosine are the same as each other. So this location is actually pi over 4, 45 degrees. That is where sine and cosine are equivalent. So here's what this means. We need to do from 0 to pi over 4, we need to do cosine minus sine. And the reason we need to do that is because the cosine graph is bigger than the sine graph until you get to pi over 4. Then to that, we need to add to this the second section, which is from pi over 4 up until pi over 2. But in this example here, now sine is bigger than cosine. So I actually have to change this around a little bit. So I have a lot of work to do here. I've got to find an antiderivative for cosine and then plug in 0 to pi over 4. Then I've got to do the same thing for sine, subtract those values, and then I have to do the exact same thing for sine and cosine the other way around, and then add them together, because really there are actually 2 different sections of this graph to work with. So organization becomes very important. Unfortunately, I'm writing on my little writing pad, so I'm not as good at dictating as I'd like to here. So I will do my best to try to make this clear. When you antiderive cosine, it gives you sine, which means you're going to have to do sine of pi over 4 minus the sine of 0. That's what happens when you antiderive cosine. Cosine antiderives to sine. Now, sine came from a negative cosine. So there's still a negative sign between these from this one right here. And then this derives to negative cosine. And again, we need to plug in pi over 4. And then we need to subtract. And then, again, sine still derives to negative cosine of 0. Hopefully you're able to follow that. So sine derives to a negative cosine. So that's why I have negative cosines right there, right? Because negative cosine would give you sine. This negative sign came from here. It's almost like I should put a bracket around that too. And then this cosine right here is pi over 4, and this cosine is 0. So, and then in my next section, I got to do the exact same thing. I've got to do the sine of pi over 2 minus the sine of pi over 4. And then after that, I've got to subtract. And then again, cosine derives to negative sine. And then the larger value is the pi over 2. Then I have to subtract the pi over 4. Yikes. So now I need to know my trigonometry very well. Sine of pi over 4 is 1 over root 2. Or, if you've learned that a bit differently, it's root 2 over 2. Sine of 0 is 0. Cosine of pi over 4 is also root 2 over 2. This is really a plus now. Cosine of 0 is 1. Okay, well, putting this all together right here, root 2 minus 0 minus root 2 plus 1. I mean, I know this is starting to get a little bit messy here, but you have root 2 over 2 plus another root 2 over 2 plus 1 means that all of this first little bit is 2 root 2 over 2 plus 1. Okay, well, 2 root 2 over 2s really gives you root 2 plus 1. So all of the area up to here is root 2 plus 1. Hopefully you can kind of follow how I'm pulling that off there. Now, it looks symmetrical, so I'm expecting the same thing here, but let's give this a try. Sine of pi over 2 is 1. Sine of pi over 4 is root 2 over 2. Sine of pi over 2, again, pi over 2 is 1. Ooh, I made a big mistake here. Woo! Hopefully you caught this before I did. Sine doesn't derive to sine. Sine came from cosine. Woo! Big mistake here. Those are supposed to be cosines. Okay, let's fix that. Okay, cosine. Let's use the same color here. Cosine of pi over 2 is actually 0. Cosine of pi over 4 is root 2 over 2. Okay, now back to this. Sine of pi over 2 is 1. Double negative really just means add. And then sine of pi over 4 is root 2 over 2. Which means I have a negative root 2 over 2. I need to subtract another root 2 over 2. And then I need to add 1, which gives me negative 2 root 2 over 2 plus 1, which gives me negative root 2 plus 1. Now, why is that negative root 2 plus 1? Boy, those two guys, they sure look like they should be the same as each other, but based on the way these curves work, it's maybe not quite the same as each other. So one of these is root 2 plus 1. The other one is negative root 2 plus 1. So I just need to add them together now. So root 2 plus 1 plus negative root 2 plus 1 means my final area should be 2, right? Because the root 2 and the negative root 2 should cancel. So there's my area. Essentially, what it looks like is you've got some area from right here and some area from right here. And when you add them together, you actually get an area of 2. Now, I just want to consider that for a second. Didn't I just do something similar to this before? Didn't we find out that the area bounded by cosine, all of the area bounded by a cosine right here was 1? Right? Like from here to pi over 2, that was 1. Just thinking out loud here. So all of this from here to here, I'm just going to color it in. This area right here was 1. But, well, I guess I really can't consider that because this area and this area here, they look like they were kind of different from each other. So, okay, I'm going to look back, make sure I didn't make a mistake before I post this video, because I did make the mistake with the sine and cosines. You can see how any little issue could really add up here. Long story short, though, the way you solve this then is you'd have to find the location as to where one is greater than the other. And you got to make sure that you subtract them from each other correctly, because you have to make sure that, like in this one right here, that you put the sine graph above the cosine graph, as opposed to the cosine graph above the sine graph. So once you find that intersection point, you got to do it twice, and then find this area in black and this area in black and add them together. So that's kind of my last example. If you'd like me to try another example with you, I'm more than willing to, because this is where things get a little bit more challenging. But that kind of ends off this section here. As a precursor to what we're going to do next lesson, the next lesson we're going to talk about how to derive some more challenging looking derivative, or how to anti-derive some challenging things, like how do you undo a chain rule? That's what we're going to talk about next. So, okay, anyways, I'm going to pause and stop the video. If I made a mistake somewhere in there, I'm just going to double check my work though. So we'll talk to you guys later. I did find a mistake. I knew I did. I don't know if you guys could sense the hesitation in my voice before this, but the fact that I got a negative number on one of these has been driving me crazy, because I couldn't figure out how I got negative area out of one of these. So I'm hoping that maybe you found my mistake before I did. Here's where it was. Right here. Sine does not antiderive to cosine. It antiderives to negative cosine. And right here, cosine does not antiderive to negative sine, it antiderives to positive sine. And I was going a little bit too fast when I was doing it, that I messed up my sine cosine antiderivatives. So there's a bit of a mistake right here. So I got to flip some signs around. So hopefully you caught that before I did. Because I knew something was funky. Here's why I knew it was funky. Right here I got an area that was negative root 2 plus 1. And I knew that negative root 2 plus 1 is a negative number ultimately, and I was like, how do I have negative area? I'm not below the axis. So right, because all of this is above the axis. Down here I'd have negative area, sure, but not up there. So anyways, let me solve this problem correctly now. I need to erase from here onwards. So let me try the second part of it again. Okay, so I need a negative cosine of pi over 2. Cosine of pi over 2 itself is, let's see, cosine of pi over 2 is 0. So, negative 0. And then double negative means to add. And then cosine of pi over 4 is root 2 over 2. All right, that's good. That's positive area. I should have positive area, not negative. Then I got to subtract the area from the second half. So now I need a positive sine of pi over 2. And sine of pi over 2 is 1. And then, let's see here. Then we have subtract a positive, so let's still subtract. And then sine of pi over 4 is root 2 over 2. Okay, so this means that I now have root 2 over 2. Double subtract really means I need to add another root 2 over 2 and then subtract 1. This makes more sense now. This works way better. Okay, a root 2 over 2 plus another root 2 over 2 gives you 2 root 2 over 2s, which literally means just you have root 2. And root 2 minus 1 still is a positive number. Now this way makes way more sense, because this area right here is root 2 plus 1, and this area over here was root 2 minus 1. And they look like they should be relatively the same, but based on the way that these graphs work, they probably aren't. Let's try graphing this here. And let's take a closer look. I'm going to do sine of x and cosine of x. And I'm going to make it go from, let's make it go from 0 to pi over 4. And then in my y value, I'll make it go from 0 to 1, because it doesn't get any higher than 1. So this is what the one graph looks like. And this is what the other graph looks like. So this area in between right here is the area we're looking for. And I believe that that is root 2 plus 1 in this section right here. Then if I change my window and I make it go from pi over 4 until pi over 2, and now I graph it. Now here's the rest right here and right there. And now I'm looking for the area between here. And this one says this should be root 2 minus 1 if I did it right. Now, I want to just find the, I actually want to make it go from 0 to pi over 2. Let's just take a look at these two things. So there's the one graph going there. And here's the other graph coming here. I want to find the two areas. Boy, I got to say, I must have made another mistake, right? Because look at these. Doesn't this area right here look symmetrical to that one? So somewhere in here I have an error. I got to find that error. Oh, where is it? Let's see. So let's take it from the top, I guess. I can make mistakes too here. Okay, cosine antiderives to sine, and sine antiderives to negative cosine. Okay, and we plugged in pi over 4, and pi over 4, and 0 and 0. Okay, let's keep looking here. So that's root 2 over 2 minus 0. That makes sense. And then we're subtracting from that a negative root 2 over 2, and then double negatives means to add. Oh, I see my mistake here, though. Because this was a negative sign right here. I have a second mistake. Oh, it's a good thing I rewent over this example here. There's a negative sign right here. So the negative made that guy a positive. But this guy right here makes this plus 1 still a negative. If any of you managed to find that mistake before I did, good for you guys. This is one of the downsides to me making videos, is that if this was a real live class, I bet you a lot of you might have found that mistake before I even got that far. So this isn't root 2 plus 1, it's root 2 minus 1, which now makes sense because both of these two bits here are the same as each other here. This is a root 2 minus 1. This is a root 2 minus 1. All right, we're finally going to get this right here. So if one area is root 2 minus 1 and the other area is root 2 minus 1, and we're putting them together, you're going to have two root 2's, and you're going to minus 2. There. That is our final answer for how much area there is. All right, and if I want to go back to my graphing calculator, this right here is a root 2 minus 1 area. This right here is also a root 2 minus 1 area. So, okay, I apologize that I goofed up that example so badly. I mean, I made two bad mistakes with my negative signs. So let me quick recap, and then you better ask me for some more help on this if that didn't make sense otherwise. If you have two graphs, but they intersect, you have to figure out where the one graph is on top of the other, and then flip-flop that, right? If you have a graph that goes like this and then like this, and I want to find the area from here till here. Well, here, this graph is above this graph. But then later, the purple is actually above the red. So you actually have to find where these two graphs intersect, and then do red minus purple, and then add that to purple minus red. And you've got to do it for two different sections. You've got to go from, like, say, A to B, and then to C. You'd have to do red minus purple. You'd have to do that from A to B. And then you'd have to add to that purple minus red. And again, you're doing that now from B to C. So you got to find this section right here. And you got to find this section right here and add them together. So, and hopefully don't make simple little trigonometry mistakes like I was. So, okay, now I'll call this a lesson. Hopefully that cleared things up for you. If not, like I said, ask me some questions. Going forward from here, we're now going to do some more challenging antiderivatives for things that would involve a quotient rule, a product rule, or a chain rule. That's kind of where our next section goes. So, okay, I'll put it on pause. We'll talk to you guys later.